A very good evening, all the participants. So it's time for starting the tutorial session. So first of all, let me welcome you all for the day one tutorial one session. So this tutorial will be taken care by Mr. Gurubelli Vikash, who is a research scholar working at Department of Electrical Engineering at NIT Rourkela. So I invite Mr. Gurubelli Vikash to take over the session. Because sir, hand over to you. Over to you, sir, because sir, you can carry on. Because sir, are you there?
Yes, sir. Yes, sir. I'm sharing my.
Yeah, you can start the session. Thank you.
Okay. Thank you. Okay. Good evening, everyone. My name is Vikash Gurugubelli, pursuing PhD final year under Professor Arnab Ghosh. Today, my topic is grid forming voltage source inverter. Actually, nowadays, what we are using, all the inverters are grid following inverters. Today, I am explaining about the grid forming voltage source inverter. And first, I will explain how to simulate the voltage source inverter in islanding mode. Later, I will explain about the parallel inverters and how they form the grid. That is the main motto of the session. This is the introduction. Electricity is the basic need, and the electricity demand is increasing rapidly due to population and economic growth, industrial development, and high domestic usage. And it is very difficult to meet the demand with conventional power generation because they are depletable and emit greenhouse gases. And in order to address these renewable energy sources have grabbed the attention of the world as the alternative source, and microgrids are one such solution to address the energy crisis with the use of renewable energy sources. And India is positioned fourth in terms of renewable power capacity. And before going to the grid forming inverters, first I will explain what is the need of the grid forming inverters. Actually, now we are using synchronous generators, and all the synchronous generators form a grid. Similarly, we are here researchers are thinking about the futuristic grid. In that futuristic grid, we will replace the all synchronous generators with voltage source inverter. So this is the new interface, and this is the scaling. For example, our conventional synchronous generators is the in terms of megawatts, 210 megawatt, 500 megawatt, but single inverter cannot equivalent to the that much rating. So for that we are scaling. How they are scaling? Here approximately some 10 to 20 inverters equivalent to the one conventional synchronous generator. And here we are talking about the location. From this figure, we can understand the difference between the conventional power generation and renewable power generation with inverters. Coming to the next slide, here we can understand the power system architecture. The present power system architecture we can show in the left side. The right side is the futuristic microgrid. Here you can see the conventional power generation is reducing, and we are using the renewable energy sources by using inverters. This is the futuristic power system architecture, and this is the implementation. Here you can see. So here this is the inverter, and this is the microcontroller. By using the microcontroller, we are controlling the inverters to form a grid. So next I will show the how we will explain about the three-phase voltage source inverter with LC filter. Here first I will explain the first how to simulate the single inverter in islanding mode. Later I will explain about the parallel inverter or grid forming inverter. So figure 1 shows the three-phase voltage source converter with LC filter. here this is the L with some resistance RF plus RR, and this is the CF with the filter capacitance, and here average ideal three-phase voltage source converter is there, and by using ABS to DQ we are so how this what is that, the conversion and this control law I will explain in the next slides. Here the input of the inverter is DC supply which come from the renewable energy sources. Coming to the next slide, here you can see applying KVL across the three-phase filter inductor. Again I'm coming back to the figure 1. Here you can see, here I'm applying the KVL. See, LF dIA by dt plus RF plus RN into IA plus equal to VTA minus VSA. So the equation, if you apply KVL across the three-phase filter inductor, we can get the equation 1. And by transforming the equation in ABC to DQ form, we can get the equation 2. And after applying Laplace transform, we can get the equation 3. And in order to decouple the dynamics, the modulation indices MD and MQ are determined. So here MD and MQ are the modulation indices. By using this, we can decouple the states. So in next slide, we can understand how they are decoupling and how we can eliminate the coupling between the ID and IQ. And the relation between the output voltage in DQ frame can be shown in equation 5. Here in figure 2, we can understand the control block diagram of the current controlled voltage source converter in DQ reference frame. Here you can see, here first you can see the, first I applied KVL across node 1. From that we can get this equation. Now you can see how I implemented these equations. So here there is coupling between ID and IQ. Similarly, IQ and ID. So there is coupling between the ID and IQ. First, we have to decouple this term. First, this is the main physical system. This is the control. This is the control block. So here you can see from this red box, you can understand the system dynamics. Here you can see ID equal to, you can see the path, you can understand this equation. There is a coupling between ID and this is the coupling term, IQ. So by using this control law, here you can see, here we are using these terms, we are decoupling ID and IQ. Here, for example, here you can see this is ID is decoupling with IQ is decoupling with ID. Come to here, I'm just here plus symbol is there, here minus symbol is there. So in the control law, we are from this we can clearly understand how we are decoupling the ID and IQ. So we are why we are decoupling. So if this is multi-input, multi-output system, 2 inputs are there, 2 outputs are there. If you decouple this ID and IQ, then we can get the 2 single input, single output systems. Then we can control the system by using simple PI controller. That's why we are decoupling the ID and IQ. Coming to the next. So here you can see after MD, we know the relation between the input and output. The VTD equal to M into VDC by 2 in three-phase voltage source inverter. Coming to the next slide. Yeah, after decoupling, we can get the equivalent block diagrams of the closed loop current control schemes. Here I'm using here one PA controller, here one PA controller to control the system in the current control loop. Here the compensator KD, KQ equal to PA compensator KP plus KI by C. Here from these equations we can understand the how to design the KP KI values, and the equation 9 shows the closed loop transfer function of the inverter in here. Actually the time period, the desired time constant for the closed loop system, and it can be represented in equation 10. So typically the range of the time constant is 0.5 to 5 milliseconds. From equation 12 shows the KPKI values. Here from from this slide you can understand the KPK values, how to design the KPK values in the closed loop current control of the voltage source converter. Next I'm going to explain about the voltage loop control. So first, before going to the closed loop control, again I'm showing the same inverter system. Now I will apply the KCL across the AC filter capacitor. We can get the equation that is same. Here also we are first transforming ABC to DQ to get equation 14, and after performing Laplace transform we can get equation 15. And in order to, here also we are decoupling. Here we are also decoupling, and the decoupling I will explain the next slide. And the closed loop transfer function is shown in equation 17. Here the closed loop is the current control closed loop transfer function. This is next slides we can understand the closed loop transfer function of the whole inverter with closed loop and open loop. Sorry, closed loop, current control and voltage control loop. Here figure 5 shows the block diagram of the voltage control scheme. Here this is the filter dynamics. This is the physical system. From this dynamics we can derive a control law. So based on that we can understand here also same. There is VSD is depending upon the VSQ. There is a coupling between VSD and VSQ. So here we are decoupling the term by using this control law. This is the control law. And this is already, we know how we got this transfer function from the previous slide. And from this we can understand the whole with closed with current control loop and voltage control loop. Now we can get the overall transfer function of the system. This is after decoupling we can get the single input, single output of the system. So why we are doing this single input, single output? We can control easily by using simple PI compensator. And here I am considering just PI compensator is only P compensator I am considering, because since the open loop system is already having one pole at the origin, it is more than sufficient for the compensators to Q proportional compensator. PI compensators can also be chosen only on the condition that it should be never be a pure integrator. And equation 20 shows the closed loop transfer function, and table 1 shows the control parameters used in simulation study. And here figure 7 shows the DQ controlled inverter in standalone mode. A is the load voltage. A is the load voltage. Suddenly at 0.4 seconds there is a load disturbance. Then there is small dip in the voltage, and within very small time it reaches the characteristic value. Similarly, you can see the load is changed, the current is immediately it reaches the desired value. So from this we can understand the single inverter in islanding mode by using our voltage and current loop control. We are controlling properly. So actually it is in islanding mode. That's why we are using current control loop and voltage control loop. For example, if it is grid connected, no need of use of any voltage controller, because in the voltage controller we are giving the voltage reference. So in grid connected mode, grid is there already. We by using PLL we can get the voltage reference and frequency reference. But in islanding mode, we have to give the voltage reference value and frequency reference value. Okay, so that's why another loop added in the single inverter in islanding mode. In grid connect, our topic is mainly focusing on the single inverter first islanding mode. Then again we are adding another inverter to the same system, and how they are behaving, how they will share the powers among them. So that is the main target of this tutorial. So the limitation in DQ frame control. So this control strategy is not applicable for parallel inverter operation. So first, up to this, I have explained the simple inverter in islanding mode. We using DQ control. Later, I will explain the remaining what is grid forming inverters, what controllers are available. Later, I will explain. First, before going to the grid forming inverter, first I will show the simulation of this single phase single inverter. First, I will show the simulation up to this 20-second slide. Later, I will explain the grid forming inverter. First, I have taken a new model. First, one by one, I will from the library. I will take one by one component. First, this is the list of components required: DC voltage source and universal bridge, and three-phase VI measurement, and three-phase series RLC branch, and three-phase series RLC load, and three-phase breaker. Bridge. Okay. This is the new model. Here, this is the list of components I will use in the simulation. First is DC voltage source and universal bridge and three-phase VI measurement. These are the components I will use. And here, actually, uh, in any system, there is one physical system and another one is control level system. So here in the physical level, the DC voltage source, universal bridge, and filter and load, all these things come under the physical system. And the control part, here I'm using ABC to DQ control. From the VI measurement, I can get the VABC. So by using ABC to DQ, I can get the VD, DQ, and similarly ID, IQ for current. And
excuse me, the screen is actually blank.
in,
The screen.
actually, this is blank.
No,
This is blank model, sir. I will.
Okay.
Visible. Okay. First, I will take the DC voltage source from the library browser. First,
So I think there is some network issues.
now is it visible?
Yes, sir. Yes, sir. Now it's visible.
Okay, now actually I'm using mobile data. Okay, I turned off my video. I think now it is visible.
Yes, sir.
Ananya, it is visible. Okay.
Yes. Yes.
Okay. DC source, the first component. Next, universal bridge. You can also try to simulate with me, then you can understand how to simulate inverter in universal bridge. I'm adding to my new model. This universal bridge. Next, I will take the three-phase VI measurement. Next time taking three-phase series RLC branch. And I'm taking the RLC load also. So I'm connecting this supply to the inverter and giving 240 volts. Next, here I mentioned the filter values and how to design this filter. You can get any standard paper in YouTube also. You can get how to design a LC filter for normal inverters. You can get easily, and the load values also I mentioned here. And three-phase breaker I will use for switch on and switch off the load, voltage measurement, and go to block. Okay, you can also try to do parallelly with me. I will do the simulation. You can also parallelly do same simulation what I am doing here.
ഞാൻ പറഞ്ഞുതരാം അതേത് വരയ്ക്കും.
Participants, please mute yourselves.
First, I am doing the physical system. After that, I will explain the controller part. For physical system, here you can see this is DC supply, inverter, then measurement, and later this LC filter. Here I am considering this L and this is capacitance of the filter. And now I am connecting the load. So this is breaker. By using this block, we can connect the extra load by giving the time. For example, if I want to switch on at 0.4 and I will in the switch at 0.6 seconds. Here, this breaker can close the switch at 0.4 seconds and open at 0.6 seconds. This is the extra load. We are intentionally giving the load disturbance to the system, and we will see the how the inverter will behave. Now I will explain the control part. So we don't have time to connect all the blocks. I will go to directly my main simulation where I can explain the controller plot and which blocks I'm using also I will show you. The controller I will use the may I told already. We have to convert ABC to DQ and that block is required. So this is the controller. I have made already. You can see this is the physical system. This is the DC voltage source and universal bridge and three-phase VA measurement. This is filter inductor and this is the load. Here I am, yes, at 0.2 seconds I'm switching the load. At 0.4 second again I'm removing the load from the system. And this physical system I think you can understand. Now I will explain the control part. Yes, from this just remember this block, then you can clearly understand how I am doing the simulation. First, this is a voltage control loop, then this is current control loop, then PWM block is there. First, I will explain the voltage controller block. From that voltage control block, then the signal will go through current controller block, then we can get. Hello?
Sir, it is not visible, sir. What you were showing, it is not visible.
Sir, voltage control and current control not visible.
Now is it visible? I will open the block. No problem. Now it is visible.
Yeah, we can see the untitled file only.
Because
sir,
I
your
think
mom-
you can start sharing.
Okay, again I will
screen.
share. No problem.
Yeah.
Again I will share.
Please do that.
I think now it is visible.
Yes, sir.
Yes, sir.
Sir, this you please explain.
Yeah, sure. I will explain. So in single inverter in islanding mode. So the inverter don't know what is the voltage and frequency. So first I am giving the reference value. This is 100 volt. This is the reference value. This I am expecting V phase max is 100 volt and the frequency is 50 hertz. So that I am giving the reference signal to the first voltage controller. in voltage controller, actually the actual reference value is depending upon the VD and VQ. Here I am considering VQ is 0 and the whole value is depending upon the VD only. So we can consider like anything. For example, the V reference equal to square root of VD square plus VQ square. So here I am directly the VD is the actual reference value. So you can give VD something value and VQ also. From that equation you can take any VD and VQ. But for simplicity I am considering VQ is 0 and I am giving VD is the actual reference value. That's why here I am giving to the VD reference is the actual reference value, that is 100, and the VQ is the VQ reference is the 0. And you can here you can see properly from that VABC we can get the, I will show you how we can get the ABC to DQ. And yes, see here from VABC, from the VA measurement we can get the VABC and IABC. And similarly here we are using ILABC also. Before filter also we are sensing the current. So we are using total VABC, IABC and ILABC in the controller. From this VABC I can get the VD, VQ by using ABC to DQ block. And similarly IABC, ABC to DQ is ID, I can get the ID, IQ, I0. And similarly ILABC I can get the ILD, ILQ. You just remember all these things, then only you can understand the control law. And then coming to the voltage controller, here this VD is the actual value and this one is coming from the here the reference value. Here the in, this is the in one is the reference value. So the VD is the actual value. By comparing VD and VD reference, we can get some error. Then I'm using PI controller, and I explained in the previous slides how to design the KPK values. And this ID, this is the decoupling test. You can see I clearly explained in the what is that in the PPT. I explained clearly why we are doing the decoupling. So here there is no physical system. Here in the controller we are what is that? We are using different mathematical concepts, or by using different logics how to simplify our system. That's why to simplify the system, what simplify our system is actually multi-input, multi-output system. By using this type of techniques, we can get single input, single output system. So then we are simply use the PI controller. By using simple PI controllers, we can control the whole system. Here, this is the decoupling term, and here ID is the. Here I am considering ID.
We request participants to please be in mute. Please be in mute mode. I request Ms. Bindu, we are please mute your audio. Let me mute. Okay. Vikash sir, you can continue.
Okay, sir.
Vikash, please unmute yourself. Vikash, please unmute yourself.
Sir, I think he has joined through our campus net just now. That might be the issue.
Yes, yes.
Sir, am I audible?
Yes,
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 sir,
you
you are
are.
audible, sir.
Okay.
You can continue.
So here the ID component is we are considering to immediately nullify the effect of the load, and this term is for decoupling the ID and IQ. Similarly, in the this is just d-axis. For q-axis also same, the how to design the PA controller and the decoupling term, and that IQ is the disturbance current IABC is by transforming we can get the ID and IQ. So every time I will explain the d-axis only because the q-axis is similar. So that's why this block is for voltage control loop. Then from that, whatever we are getting the signal, we are sending to the current controller block. Here you can see in the previous slides, I explained the here also same thing, how to decouple, and this is the decoupling term, and this is the if there is a change in the load. So if we remove VD and ID, we can remove the VD and IQ, this term we can remove, but it will slowly settle. We don't know what is happening at the load side. If we considering this load side dynamics in the control law, the controller can immediately understand something happening, then immediately it can generate the what is that? It can generate the modulating signal accordingly. So that's why we are considering this extra term. And this already I explained the relation between the DC side and AC side. The VD output equal to M into VDC by 2. That's why we are adding this gain in the controller. Just coming to the PWM block. Here I'm using yes. First we have to convert. Here we are getting the control signals MD and MQ in DQ form. First we have to convert this MD MQ into MABC. So here you can get the MABC. So then here directly I'm using PWM generator. Here you can 3-arm reach 6 pulses. This is my switching frequency, and this block by if you provide MABC, so this block can generate the PWM pulses to the 3-phase voltage source, simple 3-phase voltage source inverter. The 6 pulses I am directly giving to my universal bridge. So this is the control part. This is all this thing is the physical system, and from the physical system we are sensing the currents and voltage at different points, and by using that voltage and current, those are the actual values, and these V reference and F reference is my actual values. Now I explained how to get the desired voltage at the output side. How we get the frequency. So now I will explain the frequency part also. So here I am applying frequency here, then 2 pi is omega. Then by using this from the references, I can consider this type of block. Normally you can use simple integrator, and then you can get, if you use this type of from the references from transaction paper, I have considered this type of frequency control. You can get better response. If you can use normal integrator also, there also you can get the result. So from this you can get the what is that? This omega t. This omega t we are using all the what is that ABC DQ transformation. Everywhere we need omega t. This omega t is generating from the reference value of the frequency. So I think you can understand this control part also. So if you apply this controller, we can and now I will run the system and I will change the load. Then we can understand the how our inverter in standalone mode by changing the load, how it is behaving due to load disturbances. We will see. 0.2 seconds, I have changed the load. The current immediately increases. So now I will open the different scopes, then you can understand the controller performance. Now I am seeing the VABC, the load voltage. Yeah. Here you can see I am giving the reference value 100. So we get the can get the 100 volts here. Karthik sir, is it visible?
Yes, sir, it is visible. It is clearly visible.
But I'm showing
Yes, it is
the
visible. Visible.
okay, okay.
I think for you it's not visible, sir. If that is the
Right.
case, you can reshare it.
Okay, okay,
Please
sir.
do it once again.
Okay.
Sir, it is showing.
I think for the speaker it is not showing. So he is trying to rejoin. Please do it.
Okay. So now I'm showing the VABC.
Yeah, it's fine.
Yeah,
It's
yeah, yeah.
clearly visible.
So at 0.4 seconds, we suddenly applied the load.
You can continue, sir. It is visible.
Okay. So at 0.2 seconds, we applied load. So here we can understand the due to the load disturbance, our voltage is disturbed, and due to our control action, it immediately reaches the steady state value. Similarly, at 0.4 seconds, we are removing the load. The time the voltage increase, and within very small time, it reaches the steady state value. So now I will show the current. Yeah, at point 2 seconds. Okay. What's the problem actually? Now I'm showing the current IABC at 0.2 seconds. The current is increasing and it reaches the steady value in less time. And at 0.4 seconds, I remove the load, so the current immediately reduces. So from this simulation, we can understand single inverter in aligning mode and with load disturbance, how it is by using DQ controller, how we can get the desired value by using this DQ control. This tutorial, I hope you can understand single inverter in single three-phase inverter in aligning mode, how to control the inverter, and how to design the PI compensators in the current control loop, and how to design the PI compensators in the control loop, and finally. From this tutorial, you can understand the phase inverter in aligning mode. And now I will go through my slides to explain the grid forming inverters and different types of grid forming inverters. And I will explain how to simulate those control techniques. But that is big if you operating two inverter, the inverter and control everything is same. That's why I'm explaining the simple single inverter in aligning mode. In grid forming inverters, the number of inverters will increase, but the idea is same. So if you want to simulate the single inverter, later you can simply understand the what is that? The droop control in our VSM control structures you can easily. These are the current control loops are the very important parts in the droop control and virtual synchronous machine. Those are the well-known techniques for grid forming inverters. Now I am sharing my slides again. Okay, the limitation in DQ frame control is if we operate two inverters or n number of inverters, they don't know how to shape the power accordingly. That's why we will. This is the just not drawback. This is limitation. So, but this DQ frame control is inherently there in the droop control and virtual synchronous machine concept. Here you can see the grid forming voltage source inverter. From the literature, from this reference file, I have taken this table with different control ideas there in the literature, but these are still in the what is that? Still in research only. They are not implemented physically anyway. These are just implementing in the laboratory, and this is the futuristic grid concept. So, due to we know the depletion rate of the fossil fuels, we know. So that's why they are planning to their futuristic plan is grid forming inverters. By using voltage source inverters, they form a grid. So their ultimate goal is to replace our conventional power system with this inverter based new futuristic grid. Here you can see from different control ideas are there by using synchronous machine base. From the synchronous machine characteristics, researchers are inspired from the virtual synchronous machine. What is that? Synchronous conventional synchronous concept. They have developed different control strategies based on the swing equation. And by in Droop, this Droop also inspired from the conventional synchronous generator. There is Droop is there from the Droop character from the characteristics of the synchronous machine. The Droop characteristics of the synchronous machine. Here we are trying to imitate those dynamics to the microcontroller, so we can get the. That's why we are call it as a virtual synchronous machine. They are planning to. What is that? We are controlling the inverter such that it will act like a synchronous. So it will not act like a as a synchronous machine, but some character it will act like a some portion. For example, 30%. Based on the controller, we can reach the how much percentage led to the synchronous machine. In the VOC is the recently come up, and so many people are working on this virtual aspect of control also. I will explain I will explain the simple droop control, and then I will explain the virtual synchronous machine, and I will explain the one of the controller from the VOC. I will explain some dead zone based VOC also. I will explain. Coming to the next slide, droop control. Droop control is realized by simulating the droop characteristics of a synchronous generator in a traditional grid and controlling the output voltage and frequency of the voltage source inverter according to the variation of
Sir, Vikash, sir, your voice is not audible.
I think the internet got break again. Please
Yes,
wait
sir.
for 1 minute. He will join once again. He will rejoin. Please wait for a few seconds. We request the participants to wait for the speaker to rejoin. He will be joining in a couple of seconds. Please wait.
Karthik sir, is it visible?
Yes, sir, now it is okay, sir. You can continue.
Okay. So, and the benefits of group control methods are simple and easy implementation, and reliability is high and high flexibility. And with different power ratings also, the inverters can operate in parallel. And the equation 21-22 shows the relationship between the frequency and active power and voltage and the reactive power. And here the F set, V set are the rated frequency and voltage, and P set, Q set are the real and reactive power set points, and M and N are the group coefficients. Based on the group coefficients, they can share the power, and F and V are the frequency and voltage at new operating point. In the group, based on the variation of the output power, they can change their new operating point. For that, it will in group control strategy, the inverters will not operate at the set points. They will operate at the new points. The all inverters set their new operating point as the same. Then only it will synchronize. Otherwise, there is mismatch in the voltage and frequency. So based on the group coefficients, they can adjust their operating points accordingly, according to the variation of the output power. And figure 8 shows the group control implementation for the three-phase power converter. Here you can see, already I explained this voltage control loop and current control loop. I already explained in voltage in the islanding mode. I given the reference values, the VD reference and VQ reference and the F reference. So here by using group equations, from equation 21 we know the relation between the frequency and active power. So from this we are generating the F reference. Similarly, from the from equation 22, the relation between V and Q you can see here. So by using these group laws, I am fixing the reference values so that they can operate parallelly. Simple. If you understand the voltage control loop, current control loop, then you can easily implement the simple group for the inverters. Here I'm taking two inverters connected in parallel, and the table 2 shows the control parameters used in the simulation study. And the figure 10 shows the how they are the figure 10A shows the current sharing. Here the M is different values. That's why they are their voltage and frequency is same, but their power sharing is different. Here you can see the inverter 1 sharing less current and the inverter 2 sharing more current. So based on the group coefficients, they will share the current, and you can see the voltage. Voltage is they synchronize well, and at 0.4 second, I have increased the load, then you can see small dip in the voltage. So if there is change in the active power, reactive power or active power, there is change in the frequency and voltage accordingly. So here 10D shows the load disturbance, and you can see the current. If I'm changing the load current is increased, and you can from 10 here you can understand how the inverters sharing properly. Then recently, some universities are planning to implement this inverter droop control inverters in educational. For example, in our BTech we studied the synchronous machines and induction machines concept. Similarly, they are adding this droop control inverter as the educational control design project, and in the education also in the BTech level also or MTech level they are planning to use these things. And from this figure 11, detailed model of the three-phase inverter with cascaded droop, voltage, and current control loop. Yes, I have explained all these things. This VD and VQ are come from the what is that? These are the come from, and here he explained the group control, how to implement the group control, and this voltage and current control loop I have explained previously. And this PWM also, from the everything is common. Just we are by using group control, we are setting the values of the voltage and frequency. That's it. And here the power measurement, how we can measure the power also. Here you can see. If you once get the VD and IQ, you can get the active power and reactive powers also. And this is the filter. The main drawback in the group control is we are not considering the instantaneous powers. We are considering some averaged values of the power. So that's why this is the drawback in the group control and VSM control. And the VOC controls are the power we are considering instantaneously. So that is the main difference between the group VSM and the VOC. Now I'm going to the VSM concept. The limitation in this group control is there is rate of change of frequency is high. If there is active power is changed suddenly, so definitely there is dip in the frequency. So rate of change of frequency is high. There is a high chance of tripping of the df by dt relay. So that's why we have to control the rate of change of frequency also. That's why we are using the swing equation concept, or by using VSM, we can understand the what is that we can nullify that issue drawback in the group control. So similarly, virtual synchronous machine also inspired by the conventional synchronous machine. And from this slide, you can understand the features, inherent features and extra features. And this is the modeling of the VSM. You just see the this swing equation. From this equation 26 is the control law here. So from this equation 26, we can develop the simulation model. Yes, the frequency reference is that droop is like droop control, but here we are changing the theta VSM, or F reference is changing by using the swing equation. That's why we call it as a virtual synchronous machine or the swing equation based control. So from figure 13, we can understand the VSM control implementation for three-phase power converter. And I think no need to explain anything. This current control loop, voltage control loop, I have explained. This group control, I have explained this. From this equation 26, you can easily implement this swing equation. From that, we can get this theta or omega. Same here also in this simulation study, I considered two inverters operated in parallel, and these are the results. Almost this droop and VSM results almost same, except the rate of change of frequency. Here I am showing the comparison between the droop and VSM. By using this VSM, here you can see the rate of change of frequency is reduced. This is the main advantage by using this VSM. Yes, here the remark, the drawback associated with droop control is high rate of change of frequency. So by using VSM, which helps to reduce the risk of unnecessary tripping of df by dt relay and to limit the maximum frequency excursions by using this VSM. A limitation in droop and VSM control is we are using low pass filter or averaging. Previously I told we are using some average values. This has a negative impact on the transient response. So the VOC is the time domain controller. Now I am going to explain the VOC. The VOC is virtual oscillator control is a decentralized control strategy for islanding microgrids where inverters are regulated to emulate the dynamics of nonlinear oscillators, and the VOC regulates the amplitude and frequency of the inverter terminal voltage, and consequently inverters synchronize their output voltage and share the load power proportional to their power rating, and the VOC works on the current feedback signal and does not require any real reactive power calculations. Explicit frequency and voltage commands. Here, no need of active power, real power and reactive power and frequency voltage. So by using current feedback signal only, we can control the inverter, and the synchronization condition is independent of the load parameters and number of inverters are participating in the system. The advantage of the synchronization condition is independent of load parameters and number of inverters are participating in the system. No problem. We can the synchronization condition is not depending upon the load and how many number of inverters are in the system. This is inspired from the Lenore oscillators. Here you can see at different initial conditions also it is reaching the steady state value. Here I am considering different initial value, it is reaches the steady state value. So it is inspired from the oscillators. That's why we are call it as a virtual oscillator control. And here one theorem is there, Lenore theorem. If the oscillator satisfies this theorem, then we call it as a Lenore oscillator. If the oscillator is not satisfies this theorem, we cannot say. Once any oscillator satisfies this theorem, it will give unique and stable limit cycle, and that limit cycle will be the modulating signal of the inverter. So by using this theorem, we can understand whether that will give one stable limit cycle or not. Here I'm using actually so many oscillator types of there, Van der Pol, dead zone. Here I'm explaining the dead zone based virtual oscillator control, and here figure 17 shows the schematic of dead zone oscillator, and this is the RL parallel RLC circuit, and this is non-linear voltage dependent current source. If we apply KCL and KVL, we can get equation 30. So if this equation 30 satisfies the Lenore theorem, so definitely this will give unique and stable limit cycle. That will be our modulating signal. And here actually why we call it as dead zone. Actually these non-linear voltage dependent current source characteristics are derived from the dead zone characteristics. That's why we call it as a non-linear dead zone oscillator. Okay. I will explain how to implement these things. Figure 19 shows the implementation of virtual voltage source inverter with VOC. And if you have any doubts, you can go through the reference sheet. VOC, and similarly, same. I have connected two inverters parallel, and table 4 shows the parameters, VOC parameters and system parameters. And this here you can see. Here also they are same at 0.4 second. I'm intentionally giving no disturbance. You can see immediately it will reach the steady state steady values. Immediately the load current is changing, and they are sharing currents proportionately. Similarly, here I am considering 1:2 ratio. The inverter sharing their power in 1:2 ratio. If you can take 1:1 ratio also, it will give equal and unequal sharing is possible with the VOC. This is the comparison of droop, VSM and VOC. Here you can see the frequent and very small disturbance in the load, how they are behaving. In VSM, there is rate of change of frequency is less. In droop, there is rate of change of frequency is high. And in what is that? In VOC, the frequency is maintaining a constant value. There is disturbance in the frequency, but immediately it reaches the steady state value. This is active power tracking. Here also, the table 4 shows the specifications of rise time, settling time, steady state error with change in the load, plus 50% changes and minus 50% changes in the load. And here you can comparative performance you can understand from the table 5. And figure 23 shows the dynamic response of active power by the sudden change in the load. And now I'm going to show the experimental results. And before going to the experimental results, I will show the experimental model circuit diagram what I have used. I'm using one semicron inverter. There you can get directly, you can apply three-phase supply. There you can get the DC supply. Regulated DC value we can get here. And this is three-phase inverter with gate driver. And this is LC filter. And this is the load. I'm using LA55P current transducer to sense the current. The main advantage of this control, by using current feedback signal, we can get the desired voltage and frequency. That is the main advantage, and it can what is that? No need of any average value from the feedback signal only. It can instantaneously it will what is that act. And similarly, I'm using Opalati for generating the PWM signals to the inverter. And this is my overall experimental setup. Here this is the resistive load bar, and here you can see this is my inverter, and you can see this is auto transformer. From this in the semicron inverter we have diode bridge rectifier. So by using auto transformer voltage, we vary the by using auto transformer we can get the desired DC input voltage. And then this is Opalati, and this is my current. This is my current top view of the current sensor. And here I am here what is that? Yes, here the filter capacitor and filter inductors. And from this I am sensing the current by using this current sensor, and I am sending to the Opalati. And from at Opalati I can get the what is that control signal. After that, here I am using some opto isolators. These are the opto isolators to isolate the system from the Opalati. And here I am using one. This is not gate. Here I'm getting three signals: 1, 2, 3. By using this NOT gate, I can get what is that? Inverted pulses. Total, I will get 6 pulses. Here 3, here 3. These 6 pulses. This is CD4504 used for level shifter. From 5 to this will shift 5 voltage to 15 voltage. For semicron inverter, that gate driver is required 15 volts up, 15 volt pulse. That's why I'm using this level shifter to increase to amplify this 5 volts to 15 by using this level shifter. This is my overall experiment setup, and figure 16 shows the gate pulses to the IGBTs of switches S1 and S4. And this is the here I am changing the load. This is my load current. Immediately it will change. Immediately it will reach the steady value, and there is no change in the voltage. And this is my DC supply I have applied, and these are my references. And thank you. If you have any queries, you can ask.
Thank you, Vikash sir, for this tutorial session. And I would like to thank our participants for their patience and for the inconvenience caused from our side. So tomorrow we'll meet at sharp 9 a.m. Please be there on time and join before 8:45.